So good morning. Welcome to this last seminar this year. And today we will have the talk by Dr. Renato Dubke from the Observatorio Nacional. He will talk about fossil groups of galaxies, seeing the future, looking at the past. So he holds a bachelor degree in astronomy from the Lomonosov Moscow State University in 1990s, and then a degree in physics and mathematics from again from Lomonosov Moscow State University in 93, and a PhD degree. He was a research fellow in the Department of Astronomy at the University of Michigan in the High Energy Group from 1999 to 2003. When he became an assistant research scientist in the same department until 2009. He is currently a full research at the National Observatory. He has experience in astronomy with emphasis on high-energy astrophysics, where he worked on data reduction and analysis of satellites like Einstein, Rosat, ASCA, BIPO-SAX, Chandra, XMM Newton. He is the principal investigator of the JPAS, the Alhambra Physics of the Accelerating Universe Survey in Brazil, and scientific director of the collaboration. He works in the area of extragalactic astrophysics with a current focus on large-scale structures, galaxy clusters, groups, fossil clusters, metal enrichment, and dynamics of the intracluster medium, supercluster and cosmic filaments, supernova explosion models. So thank you very much, Renato, for this last seminar today. The floor is yours.
Thank you very much. And thank you. Am I okay? In any case, So before I start, I'd like to ask you something, because probably some of you heard that I got some virus last week in Teruel there, and so it was an unusual virus. Even though I was tested for COVID many times, it was negative, so I ended up going to visit Teruel's hospital. And before I went there, some lady, the cooking lady there said that, oh, this is not COVID, this is a virus that everybody's getting. And I was, well, okay, thank you, doctor, cooking lady. So I went to the hospital, and the doctor there basically said the same thing. So in principle, I got some virus that everybody's getting. And I'm just showing that, and have been testing anyway, every day, just in case. And if you don't mind, I will take my mask out. This is 100%. Everybody's comfortable with that. Are you too? Okay. You may just get the virus that everybody gets. So you'll be part of the group. That's right. So the second thing is that, yes, many of you actually know me as through JPAS, because the IA is a cornerstone. It's one of the founding institutions of JPAS. And I am a science director there. But we just had a meeting last week, and I'm sure you know a lot and heard a lot about JPAS. So I thought of doing a talk on something else, some work that I've been doing for quite a while, and that it has a possibility of, and we hope, to enhance in the JPAS and JNAP collaboration as well. But it's something a little bit different, which has to do with studying this early formed systems. They're generally called fossil groups, originally called fossil groups. And for a long time, I had been proposing, getting some data, building up data from different institutions, from different instruments in X-rays with Chandra, with XMM, Hubble, in optical, and some spectroscopic information as well with Gemini, and trying to find a sample of the systems that was actually, I call them bonafide, because they seem to have all the weird properties that fossil groups were supposed to have. Well, originally they thought they had this very bizarre properties. And I'll explain why there are larger samples of fossil groups, but they are generally used, people are using very often just the magnitude gap between the first galaxy and the second galaxy. And I'll argue a little bit, and this is just not me, that this is not the best way of finding the systems. And so people have been going around, and we have, now I gave it a name, MIXDEGS, Multiwavelength ICL and X-ray detection of early galaxy groups. And you really might be right. It's still pending approval, the name that I gave them. Nobody was against it. Which involves a bunch of people from a bunch of different institutions. They include the ON and the IAA as well. Okay, so. All right. So I'm talking about this in part. I returned to this a few years ago because there was a big change. I think there were two changes there. One was a particularly unexpected one, which was a work that has been, the Yoli and myself have been developing since she went to Brazil, which was the study of the ICL. And this actually shone a light in the FGs that was very welcome and very interesting. And so I'll talk a little bit about that, about the cycles that Yoli led the work. And I'm sure that you've heard talks about this before. I'm not going to enter into too much details, but I'm just going to briefly mention. And our application for this to the clash sample, which we found, and this was very unexpected, amazingly surprising, that we found particular characteristics of it's not exactly the spectrum because we're using colors, Hubble colors, particular features in the ICL color distribution that could tell us in principle if the dynamical stage of clusters of galaxies, which is a notoriously difficult and necessary problem, has been open forever, including for cosmology. And this has this opened a very interesting window that so far remains open, and we are pushing this as far as we can to see how far can we go with this. And like I said, it was so far the sample is not large, have maybe 15 total systems, but so far it's 100%, right? And I'm going to mention a little bit of one of the latest challenge that is one of the clusters that Yoli has been doing, high Z, testing high Z clusters to see how it works over time. And from time to time, you have a challenge. Is this actually breaking the merging fingerprint or not? So I've discussed a little bit about this. And then the application of this to the fossil groups, to this sample that we raised using the ICL spectroscopy in X-ray, spectroscopy in optics, imaging. And the main paper, the pilot paper for this, which, and this is a pretty interesting, and was actually surprising to me, that there was this whole discussion about fossil groups being old or not being old, because originally they thought to be old by their properties. That one of the characteristics of fossil groups is they have a huge galaxy, a BCG in the center, and a complete paucity of bright galaxies around them, such that the rank 1-2 difference in magnitude is 2. Even though this number is a little arbitrary, it means that there is a lack of bright galaxies in the center. Originally, they were thought to be galaxies. They called OLEG, overluminous elliptical galaxies, because they have X-rays around, and was only one galaxy. And OLEG, not surprising, was described by Alexei Viru. And then they end up finding galaxies all the way around it, far away. And they thought this is obviously not a galaxy, it's a group. And it's not really a group, because some have temperatures and masses comparable to clusters of galaxies. Okay, so and I'm going to go back about this, but one of the main contradictions with them is that they don't have cool cores, or they have very poorly developed cool cores that you find in clusters normally. And Relics systems tend to have cool cores. A cool core, for those who are not accustomed to the X-rays, when you look at a cluster in X-rays, the gas that permeates the galaxy, we call them intracluster medium, even though this term needs to be revised. Now the ICL is also part of the intracluster medium, but this is a very hot plasma with temperatures on the order of tens to hundreds of millions of degrees. Okay, so the main emission there, they're fully ionized, almost fully ionized. The main emission there is through bremsstrahlung, and it comes in X-rays. So you see an image of a cluster in X-rays. You see this blob there. So the issue is that the bremsstrahlung is proportional. The emission of a bremsstrahlung is a function of the density of the gas squared and a weak function of the temperature. Okay, so in the central parts of the clusters of galaxies, the density is very high, is higher, so the emission is very strong. It's brighter in the center, so it loses energy a lot, very fast, and it cools off. As it cools down, the gas, P's and KT, right? There's a pressure gradient. The pressure drops, and you have a pressure gradient that will bring material from the outside in, which will increase the density more, and will emit more, and will cool more. Okay, so if you let this go, eventually people thought it would go to a cooling catastrophe, right? But it doesn't, because the AGN there gets active and starts hitting the gas through jets and other ways, so that this, which used to be called cooling flow, stops at about a third of the average temperature of the cluster. So the thing is that if you leave a cluster there, eventually you will develop this cooling in the center. The systems are supposed to be very old because they thought originally that all these galaxies were around the BCG were equal. Well, by dynamical friction, you start slowing them down, and then you have tidal interactions that will, destroy them. And so they were very old. That's what they call fossil groups. But they didn't have cool cores, which is a main contradiction. Okay, so so many people, including myself, thought they're not old. This is nonsense. After this work, we concluded, wow, they are actually old because of the introduction of the ICL, and we're going to get there. So I'm going to show some preliminary results of some other fossil groups from our sample there, and some of the hypotheses that we have now for solving this presence of hot cores in fossil groups, comparing with data from the Suzaku. It's another X-ray satellite. It has a pretty good spectral resolution. And this work is led by Rebecca Battaglia, which is my previous grad student. She just finished and is going to CEA-Saclay in January. And some applications to JPass and GNF. So this is the people basically so far. Actually, there's one person who's missing here that came on board a couple months ago, which is Francois Mirnier as well, which is a great person to add in because he knows how to deal with RGS, which is a very complicated spectrometry in XML. Okay. So about the ICL, and I don't know if you've heard this before, just tell me. Keep moving. And by the way, if you want to interrupt me, that's okay too. Anytime. So, like I mentioned before, Yoli, when she finished here the PhD with Chichu, they developed this Chebyshev polynomial fitting tool that was amazingly good. And when she went to work with me, we decided to invert this and think, what about getting the galaxies? Any galaxy can be modeled by the chefs very easily, and I'm sure that you have seen this before, and you can take it out. So why don't we actually forget about the galaxies and look at the ICL? And so we start trying to develop this thing. The first one, Yuri led this work amazingly. It's not a trivial thing to do at all. And of course, the choice of clusters was that we decided to start with was perhaps not the best cluster. Well, who knows? It's the Pandora cluster, Abel 2744, which is a monster, and it's one of the frontier field clusters. And if the data from GSFC is actually public, it's incredible to take a look at this. And this is the cluster. It is a quadruple merging system. Actually, logically, it would be a double merging system, 4 clumps that simultaneously collided, more or less perpendicular to each other. And you have all kinds of phenomenology. One is like that, the other one is like this. And in X-rays, you see basically a stream of gas this way, another one here, and you see some really interesting phenomenology. I don't want to go into a lot of details in this. You see gas without dark matter, you see dark matter without gas, all kinds of stuff. So this was a pretty tough one to do, and it's good to be tough because if you can do for that, you can do for everything else, right? And that's what was the original target was, and this is what was published. This is in the Ioli and myself 2016. That's the original, is a very solid, robust paper for the technique. And this is the original image, Hubble image at the red. And this is the after passing through cycle, and this is the ICL distribution. So this was working fine. And then we decided to take a look. What about really was part of the clash group as well. So let's take a look at the clash clusters, right? See, start applying things over and over again. And that's the part that was surprising. Here is basically you have on this axis the ICL fraction, and this is the frequency, the wavelength here. And this cluster, this is the clusters, the 3 filters, HRC filters. And the red ones, they are emerging systems. And the blue ones are supposed to be the relaxed systems. Although when I use relax, I don't fall into the trap of defining what a relaxed system is, because I don't think anybody really knows. But I mean, observationally speaking, it's very easy to say when a cluster is merging, not so easy when it's dynamically undisturbed. But several parameters for separating the 2 groups were used. And this I have here presence of radio halos or radio relics. They are typical of merging clusters. Concentration, generally the more concentrated, the less active. Presence of multiple bright cluster galaxies is a general indication of disturbance. X-ray symmetry, you can look at the image in X-ray, the power ratio, basic expansion of this, and see the kind of substructure you can find there, centroid shift, and so on. A lot of this came from Megan's paper, Megan Donoghue. And so there were many indicators. Saying this is classified as a merging cluster, this is not so merging at least. And the surprising thing is that this is the error, this is the error here, that's the value for the 2. Of course, we have only 3 points, but it's a lot of systems, right? And we can see that the relaxed clusters, they have more or less a flat color distribution. Yes?
The ICL fraction is with respect to the total light in the system, or is it?
Yes.
The fraction, yeah.
Yes, total light. Yeah. So, and thanks for that, because that can be confusing. It's not,
not relative.
Right, yeah. So, and this has this, all of the of the merging systems were kind of here. And that was very unusual. Why are you have this axis? In this case here is not rest frame yet. I'm going to show you a rest frame in a second, but that's what we saw in the very beginning. So I decided to get this for historical reasons. It's the more emotional to see that. So what's going on here? So when we plot this in the rest frame, only for the merging, only the merging clusters, you see that this they are kind of peaking around somewhere between 35, 45, around this region. This is the redshift of the systems, and again, ICL fraction, and there is this axis only for the merging clusters. And here you have basically the average range for the peak emission of main sequence stars. There, just for comparison. So what would this be if there were a main sequence star? Right? So it's somewhere between A and F, somewhere about here. Yes? Okay. So this definitely opened, we're trying about physically how to do this. Raza, you may know this plot, since it's yours. We came up with after Scratcher has a long time, with an idea that since there is this gradient of age and distance for galaxies, it's from Khalifa. If you start by just tidal dynamical friction, tidal destruction, right? Tidal interactions are removing stars from the outskirts of galaxies, and if there is a gradient of particular stars in galaxies in general, so you may tend to start getting more stars at a particular time first. Okay, so if there is a merger and the merging enhances the ICL production, removing the stars, and there is an average gradient of of particular types of stars in the radial with galaxies, you may just throw those stars up there first. Okay. Of course, there are many caveats here, and it'll be interesting to explore this a little bit more because Khalifa, I think those are all field galaxies, so they're not cluster galaxies. And we're talking about clusters of galaxies. So it's not clear exactly how this distribution would actually be if galaxies were in a cluster for a particular amount of time, and then the two clusters collide. We don't know. But that sounded like a nice narrative for this particular process. And since the stars here at the end, they're more towards the, you go from G, the average, you end up with AF, this would be more or less the peak emission that we could be seeing in the ICM. You're taking a lot of this stellar population, you're throwing them out there. They're suddenly becoming their brightest because they live about 4 gigayears, 5 gigayears. You take them at say half age, 2 gigayears. So they live for 2 gigayears. They produce this excess that we call later bi, the blue ICL excess. And then after a few 1 or 2 gigayears, they start either becoming white dwarfs or becoming some red dim galaxy somewhere else, and you return back to what we thought would be the relaxed system until the next merger comes in, and so on. So that is the narrative that I've been so far thinking about. And of course, we kept piling up more and more systems. Every time we find one that is interesting, we check it out. And Yuri has been dealing with some of, I think, is the Relics. This part of the Relics groups, right? Whereas clusters have some more filters on the very red, and on the very red, they tend to go up as one probably would expect. If you think a little bit, probably all the stars that become redder, they keep accumulating the clusters there, even though they are not very bright. And one of our hopes is that perhaps this is going to be great to do scaling relations with respect to the mass of the cluster. We actually know that component in the realm. And this is just an example. One of them that was particularly mysterious and intriguing, and now I have been concerned about it, is this Software Telescope 015. And you have this two, and there's another one from the Atacama telescope, 0102. Those are the black ones, and you can see the black ones, they go up as well, when you have a blue axis. However, those are clusters that redshift 1, or at least this one is 1. This one I don't remember, or something close to that. And it keeps going up, but the bluer part, and this is pretty farther than the other ones we have been seeing, they have a blue component a little higher. It has not declined yet. Eventually, probably, they'll lose this spark here. And the problem with this is that some other people said the SPT 0615 was an incredible example of a very far away cluster that was realized. So that's what got us curious. And this is one of the initial papers for this cluster. And this is Monique Arnaud et al. They got the Planck. It has a different Planck name and the SPT name. And this is the system seen by Planck. This is the X-ray seen by XMM, and that's a surface Planck profile. And so I'm paraphrasing here, kind of. This system, possible that this is a cool core object as Z1. Such objects are expected to be rare, and no cluster at this redshift has yet been found to contain a resolved central temperature drop that could confirm the presence of a cool core. And this one, there was a claim for a cool core of this system very far away. Rational, okay? Yeah, okay. So this is 2017, many years later. This is an observation with Chandra for the same system. They got 200 kiloseconds of the system there. And among many 500 systems at high redshift, they are SZ clusters. And this is the only one that was observed with Chandra, the other ones with XMM, for the simple reason that Chandra had better data than XMM for this particular cluster. And this was Bartolucci et al. 2017, and this is a deep projected temperature profile of the system. And keep in mind, this is R500, which is about about the megaparsec for this system. It's a pretty hot system, 10, 11 keV. And you see this nice, well-behaved, and cool core, relaxed. That looks like there's a cool core, looks like it's relaxed. And there's a many mentions of this. He used this, and he also used, stressed a lot the centroid shift. So how far the X-ray center is from the BCG. As defined by, and that's not real centroid shift. If you go to real centroid shift, and I did, it's actually bigger. And there are two X-ray centers, X-ray peaks. But what they do is to get the average circular aperture, and they don't go to the actual center, they just extrapolate them. Okay. And so this is the only one. And again, in this business, it's kind of funny how people try to separate merging from non-merging. They use some parameter, in this case, centroid shift. And somebody, in this case, was Pratt, a long time ago, said, well, we can divide more or less our sample if we assume that one bigger than one is not relaxed and smaller than one is relaxed. And then the next person comes in and assume that that is an actual number and not something that was conveniently used to more or less separate two possible populations. Pratt himself, he says very clear, this is, you look and you can more or less here. And the next one comes, oh no, one. And so this is the system, right? So measure with Chandra, it's below one, it's actually borderline. And with XMM, it is below one. Keep in mind, XMM has a way significantly worse spatial resolution than Chandra. And so they conclude this, okay? So it must be relaxed. So because of this paradox, I decided to take a look at this in the last couple of months, or three. So I look at the Chandra, I got the same observations actually. And this is the system, okay? The first thing that you notice here is that it's definitely not circularly symmetric. It is highly elongated towards this direction here. And if you look at this is 2018 paper, the lensing, this is the system in optical, and this is the critical lensing curves right here. It is the same angle, okay, about that. It is as if the cluster was being squished like that. But that's not all. You see significant substructures right here. There's an axis emission right here. And there is also this whole region in the south. There's it has more emission than one. So there's already there something weird for a relaxed cluster. So I'm going to be very brief about this. I don't want to enter too many details for this part because it's not the most important one. But I basically did the same thing that I'm doing the same thing with the same radii that Bartolucci was doing in that plot over there in red, except that I don't see anywhere a table where I had the values. So I had to get a ruler and do, like 0 times, measure the radius, and I think it was pretty close. The deprojected value is the green-black one, right? The red is a projected one, and the gray is a projected two. The red is basically these two regions stacked together. I used, like he did, centrally concentric circuli all the way there. And this is one background I use, this is another background, but this is a detail. And so here there is definitely the temperature seems to be cooler, okay? But before you get here, it's not a smooth decline. There is a ring, the second ring there, which is, okay, the second, if I bend these two together, there is about here, there is this excess temperature that if you deproject gets to really high temperatures, over 14, 15 keV, something significant. And I was puzzled why we're getting such discrepant results, and the rest we're okay. I don't know, and I really don't know if it's the technique for deprojection. I use a very basic deprojection technique, which is I'm just piling up models all the way. They call the onion ring method, right? And the only difference is that I use local background and he used some kind of model background that I have no access to. And also you notice an increase in abundance here in metallicity from the outside in, okay? And so this actually suggests that you may have actually something cooler in the center, but not necessarily this is a relaxed cluster with a group core, right? It could be something else. These two backgrounds I used was to try to get a better version of the last bin. Okay, because there could be some contamination from this background being too close to this one here, and there was actually, because with the black one, everything is corrected. So the only one that changes is the very last bit. Okay. So let's keep going. So I kind of reviewed an old adaptive smoothing code for X-rays to see if I could get some more information about this. And this is adaptive smoothing. So it goes to a region, get a circle, see how many photons I want there. And then if it's not enough, it grows the circle, keeps doing that. If it is enough, it stays with whatever is inside. And I could get an interesting map. This is a spectral altogether here. So it's maybe a little confusing. So this is the temperature map. Okay, blue is 10 kV or less. And the more it gets to yellow is 16, 17, white is super hot. Those are the black here is the same contours I showed you before, the X-ray emission. And this contours in green are the regions that I consider to be significant. Okay, this has an error, basically delta temperature by temperature. Inside this green thing here is about 15%. So temperatures have an error of 15%. Here we are talking about 25%. Yeah? 25%. If you go here, it's not, you don't believe anymore. Because temperatures are like 50% error, 100% errors, so you don't know anymore. You don't have enough counts, there's nothing you can do. However, in this inner region here, you can see a lot of stuff, right? This region is 15% temperature difference. So you can see the cooler region here, and not just here. You see cool region here, all along this this axis. You see the cool blobs, and you see this red blob here on this side. That if you do, and the white circles are the radially circular symmetric distribution that we showed before. And we, myself and metallurgy, have a big difference around this ring here, where there is this hot spot that I don't know why this was missed, but with this map, you can see that the problem is about here. So this region I cannot say anything, but you can see there's an excess emission here, which is cooler. And this is actually more or less marginally significant as well. There's more structure here. This arm is actually hot as well. So putting all together, this blob here that I'm finding with high temperatures is significant also coincides with another BCG or a pair of BCGs. They're actually coming same redshift, very similar redshift. They may be coming 500 kilometers per second or something like this. I would say it's coming towards this direction, like here, and this is where the main BCG is with a bunch of lensing stuff and so on. And so I think that pretty much settles the case that this is not a relaxed cluster. Something is happening there. There's at least one margin coming right now, probably two, because this tail, hot tail here that we saw is probably to a margin as well. So again, the ICL cycle works. So it's not buzzing. So about fossil groups. Again, coming back, some of it I already mentioned to you. Why are they interesting? And right now they are more interesting because people got more data about it. They have very large BCGs. The AGNs are very inactive in fossil groups. They have a paucity, lack of bright galaxies under half the Virial radius. They have relatively large masses. The masses are not anomalous. The masses correspond to the velocity dispersion. Okay, they're high. For a lot of them, but they are still physically compatible with one single gravitational potential. They don't have a lot of substructure, if there's any. They have high concentrations, and initially it was just C200. People using cosmology, Wizard Wechsler. C200 is basically the radius divided by the R200, right? By the core. And so if they are very high, but it's not just the C200. You have X-ray concentration as well. You get surface brightness from some region, 400 kiloparsecs, something divided by the one is 40, and you get some concentration there. So they are concentrated. And high concentration, cosmologically, there are some studies that show that they correspond with earlier formation times. Okay. With earlier formation times. And they often lack cool cores or have small cool cores, not what you expect from a Relics system. And some of them, the ones I'm showing you, they have hot cores. They have very high central metallicity, which is typical of cool core clusters. Okay, clusters that generally emerge, they don't have central high metallicities. So they seem to be older system. So there were many selections I mentioned before about using the magnitude gaps. There's a lot of things here to read, and that's why magnitude gaps alone, they're not very good. Okay, it's not a necessary condition for the system to be, especially because the magnitude gap of a system is highly transitory. If you do a sample based only on this, there'll be a very small purity on the sample. There'll be a lot of noise. It's going to be very difficult to get properties that are exclusively from this particular systems. There are some different phenomena that can change this. In fall of new galaxies may change the magnitude gap. The opposite happens when the galaxies merge with the BCG. Just the orbital motion of member galaxies will produce a variance in gap that can be up to 2 magnitudes. Okay, just the orbital motion. You look at them in projection, oh, that's a magnitude gap, that's a fossil. That's not true. So one of the simulations that were interesting, Lee and Chen recently did a simulation of fossil systems, cosmological simulation, and studied them. They were a little bit less massive than the ones that I'm showing you. But they also showed that selection based on magnitude gaps has very low levels of purity. However, magnitude gaps are cheaper, right? You just need to look at it, and then other things like measuring concentration parameters or getting the X-ray concentration, things like this, they require multiple observations for your sample. And so it's clear why people choose that. So we built this sample. Then we start with the max BCG cluster catalog, and then we put the field, on top of the magnitude gap criteria, low richness, high low mass systems. We followed up with Chandra snapshots, a lot of them, to see if they have cool cores or not. They look like they have or not. Later it was confirmed with the XMM data, and we end up with the sample that I mentioned to you in the beginning. It's just a page that shows where we are with respect to the ones that have data from everything, like XMM, Chandra, HST, Gemini, Suzaku, and whatever else we need. And some they're missing, and some here that we have started looking at recently. So we got approved this last round for Chandra for this FP. What we call FP here is fossil group progenitors, because we like to see what happens to the system, the properties of the systems just before they become a fossil group. It's like the last galaxies merging with the BCG, are the properties the same? And this is something that has not been very studied. It was Lucas Johnson did a selection for this based on lensing, because they tend, since they're concentrated, you can find more lensing on them. Okay, so I'm going to show you very fast, very briefly, the results for the pilot study that we sent this year. It's published this year. And this is RxJ for short. I'm going to call them 1007. This is the image. Those are the two. This is the blue. That's the green, the 606-435 images of the systems, the fossil group. And this is the ICL as measured by cycle. One thing that is interesting, and I was talking to Julie a couple of days ago, is that now that I've seen some of the ICL from JWST in this meeting in Terrell, and they see some things that are really bizarre. They have some surface brightness discontinuities in the optical, in ICL, which is kind of weird because it's stars, right? It's not gas. And I was wondering if this is actually we're detecting this sharp edges. And sometimes you find things like holes there, rings around. And that Chema was mentioning that this probably has to do with this flash back radius that people find in clusters. Nobody knows. This is just fresh data. So like I mentioned, I talked a little bit about the code before. That's an X-ray view of it. That's an XMM view. That's half R500, and that's the contours. And I'm going to skip for the the results. So the temperature is in the outskirts. This is XMM derived temperature, except for the red bin here, which is Chandra snapshot measurements. You see the temperature goes from 1.5 to 3 keV in the center. That's 30 million degrees. And again, the abundance goes basically from the usual for clusters, 0.2, something like that. And when it gets close to the center, it has this very strong peak. It goes to super solar values. Those are the actual values for that. And so putting there in the plot that I just showed you before, I want you to focus here only on the black squares, okay, these two. Those are the merging clusters here. Those are the blue, the relaxed clusters. Forget about the green. We don't need to talk about the green now. The black is the photo group, the ICL fraction we have there. Not just, it does not show an excess there. It looks like it has a decline. It has like an anti-excess. Okay, it looks like the red part of it is going up and the blue part is going down, which is kind of what you expect if you just let the system be there forever. Like the blue, since this is normalized by the total light, that includes the blue, right? The light of the galaxies there. And they will be either quenching or disappearing from time to time. And this is gonna start to make the blue ICL fraction to go down. And that's the second thing that was pretty amazing when we saw this plot for the first time. You say, they're really old, the systems, So, okay. So let me try to get this a little bit. Let me see if this can be understood, because we're trying to see how this works. If you have a fossil, we have a system that is merged. So you produce ICL, and we saw this before. When you merge the two systems, you get the ICL, especially in that particular blue axis, and you throw it out. Right? So knowing that mergers increase the ICL is something that has been thought for a long time. But if there is no merging, the system is they're stable, no interaction, you still have ICL being produced just by the orbital motions of the galaxies inside. Right? You still have a second way of producing this. Now, the logic here, we separate this process in two types. I call those which increase together with the system's mass. The second method that I showed you does not, it's just ICL going up. The first one, when you got two clusters of mass m each one, they have also the ICL, you pile them up, you have the sum of the ICLs, the sum of the mass, plus the ICL is produced during the process of merging. Right? So that's the increase in the ICL per mass ratio. The rest would not. If there was no ICL, extra ICL produced in a merging system, and I got the two of them, I just merged them together. So, the ICL and the mass would be growing at the same rate, without making a difference. There is a little bit. If you get a cluster that's relaxed, not merging and producing ICL there, the mass stays the same, the ICL keeps. The older it is, this ratio of ICL to mass should increase, right? So, maybe this with you have these two types. If two clusters formed at the same time, following different merging trees and keeping similar average merging histories, so similar overall mass distributions of the halos and subhalos, one would expect them to roughly have similar masses and ICL to mass ratio, or if you wish, you can call specific ICL. So it's the amount of ICL per hydrogen, per atom that you have there. At any particular epoch, with a steady growth of the latter, even after all surrounding bound halos collapse into the final system. On the other hand, if one of these systems, which I call S1, formed earlier than the other one, they have the same mass still, okay? The same conditions, everything is it's an idealized model. The S2, it would achieve its maximum final mass, swipe out all the halos around prior to S2, and start growing the specific ICL only by this process, okay? That you don't grow the mass, only the ICL type B. So at the moment S2, at the time the S2 had its last merger, S1 would have the same mass, but a higher specific ICL per m per mass than S2. Okay, so this could be a way, perhaps, of testing this. NFGs would be S1. And you'd expect if this happened that they have been for a long time piling up ICL, keeping the same mass. So the ICL per mass should be higher. I don't know, after we thought about this, I was not expecting to have such a huge, I was expecting to see something like it's going to be slightly higher than the other ones. And no, it was really huge. This is that system. Okay, so this is now is the ICL fraction divided by mass 500. Okay, so this is the specific ICL. And this again, this is the filter. Okay, the filters of the Hubble filters. Those are the systems you've seen before. Okay, all of them here, the more or less relaxed, the merging, they're all kind of here when you compare to the values that you find in the fossil. Okay, we're talking really. This is the most relaxed cluster in the clash, I think is the 370, and this is what the fossil was. Okay, this was a pretty impressive result. This actually, I'm not sure it's worth going through. This is simulation from Lee and Chen. They're basically, they came to a similar conclusion, although some things I stroked through here because it's not clear that it fits with what we're observing. But what they saw in simulation is something similar. The normal group, you have the star-forming galaxies appearing somewhere at redshift 2 and 3, and they keep increasing. That's the gray here is the halo. And then at some point, as z equals 0, they start quenching the star formation here and they get a few galaxies coming here. The fossil group starts with a bigger halo, okay, a more concentrated and bigger halo, and it accelerates this process, okay? And it forms earlier, and when I say forms, people say it doesn't form before the cluster. The universe has one particular age, that's it. Things are forming more or less at the same time. What we define by formation here is how much of the final mass do you get at a particular time, right? So generally people use 50%. The moment of formation of the system, the cluster is when it achieved, the halo achieved, say 50% of the very final, when it swept out everything that was around. So that's what people generally talk about formation. But so they would start with higher halos and they would get this process happening faster. What I disagree here is that it suppresses star formation within a few Virial radii. But says here, typical group, star formation galaxies in green begin to cluster redshift 3. They continue to accrete matter and to form stars between 1 and 2, and then until it hits the gas enough to quench stuff. Fossil groups also start forming a high Z, but they assemble their halos earlier. Our FGs come from more concentrated initial density fluctuations, leading to a more massive central progenitor, redshift 2, which quenches the formation early in the central halo. So far, so good, but I'm not sure about the second part here. And also quenches everything up there. And I'm going to go back to this point at the end of the talk, because we have some evidence that maybe that's not the case. The star formation of fossil groups tend to be consumed with central halo earlier than typical groups. And the end result is a group size halo, the same halo mass, but a lower stellar mass. This from the simulations. Okay. One more group for you. Next one, RxJ0856. Actually, we have a third one, but we're still waiting for some SPECSI to actually pile that up, because the ICL is, the way that the ICL is measured is very dependent on the proper membership, the membership of clusters, because this is very important for fossil groups, because sometimes one bright galaxy mixed there may alter everything, right? Because there's so few bright galaxies there. The same one, same behavior, worse. The diamond is even worse than this one. It's more extreme, 0856. And if you look for the specific ICL fraction, this is where you are. Okay, even worse than the first one. Of course, I don't want to generalize from 2 to all of them, but it's going in that direction so far. So the question about this that I'm going to focus, is going to be the last part of the talk, is why, if the systems are so old, ICL shows this, they're super old, have been for a long time, just growing ICL without increasing mass. Right? They don't have structure. They have nice center abundance gradients peaked in the center. Where are the cool cores? You leave something there for a long time, you will develop cool core. Right? So this continues to be a puzzle. And so those are the temperatures that I showed, the 1007. This is the 086. No, that's 1410. Another one that we have. They were almost finished with making sure that the ICL is correct before we publish this. And the third one that I showed you was 856. And you can see here there's also temperature. The outer bin is like 1.1, and the inner bin is 2.2. So it goes up for a factor of 2. I don't have the plot here. So just these numbers that I show, but the other ones I showed the plot. So perhaps the way to do this is to look at the abundance ratios that I think is very popular around this galaxy evolution, stars, and so on. People love abundance ratios. In X-rays, you can also get the lines, get the abundance ratios. And from this, it has been known for a long time that you can find out what kind of type of supernovae or the group of supernovae actually was more predominant where you're finding that particular measurement. Right. So in a simple way, if you get core collapse supernova, they generally produce way more alpha ratios, although not all of them, let's say oxygen, neons, than supernova type 1A. They produce way more of the iron type elements. So, and that's what Rebecca was doing, her final thesis recently. And what we find is that, and it's not that easy because the spectrum, we need more, of course, we need more data, but we still can take some conclusions from it. The fraction of iron mass that's produced by core collapse supernovae for this system, 1007 is about 50%, big error bars. This is 1410. In the center, it seems to grow to 60%, more or less. And 0856, it's, and even the center is over 19%, probably 20, 30%, but in this range here. Okay, she used two models. I can go back to this if you're curious about the models that were used. But what she did was to do a comparison of these systems to systems that we know they are relaxed, but they are not fossil. Okay, to see what would you expect in contribution for supernova core collapse in the center. And she used Suzaku data for a bunch of systems. Here, the 18 systems, most of them, almost all of them are cool cores shown. Some others are mild cool cores, and looked at the abundance ratios. And this is the plot for the inner regions and outer regions. Suzaku doesn't have very good spatial resolution, but that's okay. And you can notice that, first of all, most of them have an iron enhancement in the center. And if you look at the ratios here, you find a mild but significant trend in terms of how much more supernova type 2 have, not the number, okay? Not the number, because one supernova type 1A sends 10 times more iron than supernova type 2, but also sends iron, okay? An iron is an iron. The question is, how much of the fraction of that particular metal came from this type and that type of supernova, okay? So it was mild, very significant, but it's on the order of 17% in the center. And that's in this region here. The errors are much better because we have a large sample, and Suzaku has great spectral resolution. Then, knowing that we have a slightly higher fraction of core collapse supernova, and so core collapse supernova, they must have exploded more or less recently, right? Supposedly. Maybe the chemistry of the gas was changed by the supernova, which means that they deposited energy from the explosions of all the supernova in the central parts of the fossil, and that energy was enough to raise the temperature in the center. Maybe. So that's what the calculations were about this. We're talking here about 10 to the 59 ergs, more or less. And for each one of the systems, I'm not, of course, the errors, and everybody's going to say here, the error is really bad, but it doesn't really matter the precise error. What matters is that it is kind of, it seems to be sufficient. It's kind of in the ballpark that this particular explanation may be what is causing the central heating in this fossil course. Okay. it is in the same order. So at least we can say that wet mergers because you'd have to have some kind of galaxy with gas being eaten by the BCG. Then you have fuel to start producing supernova, right? And then you warm up everything, change the chemistry of the gas, and then instead of getting the cool core, you get at least a longer period until the gas eventually cools. So let me go before that. So the last part here, and this is just where we are right now. There are many questions that we're testing and we're thinking about testing. One of them is what's the frequency of wet mergers? Were they higher near the formation of the FG? Was it like the last merging of the two galaxies? It had to be a spiral galaxy that merged and produced this thing? Or maybe there's a lot of small little galaxies that actually get to the center. And if they do, why aren't they quenched? Right? You'd expect like to have gaseous galaxies to be more prominent in the outskirts of the systems and not near the BCG. Maybe if you remove all the other galaxies from around the BCG, they actually are not quenched. You know, those are open questions that are very interesting to test. That's what I say here. Can positive galaxy in the center stop the quenching? There should be an accumulative reflux. That's something that I have been trying to measure, propose to measure. Because part of the stars, from the blue axis, part of them are going to become white dwarfs, planetary white dwarfs. So they're going to live forever there. And they're going to have a peak that is in the UV. And maybe there will be a UV excess that could actually give us material enough to know how many of them are there. Okay. We have a deficit of UV satellites now. So I'm using some of the old ones. So yes, this is very important, and this is what I want to go to. Eventually, we got to JPass can be very important for this. Is that the ICL marker, this fingerprint of merging, is perhaps the most clean, the most powerful way of telling the dynamics of clusters, exclusively from optical data. Okay, and this is perfect for surveys that depend on optical data. You analyze a system of clusters of JPass, and people do go through a lot of trouble to try to remove the merging systems out of there. They take the core out. They do all kinds of stuff, get specific rings, and so on and so on and so on. If you already know by the optical that these systems are merging, you just remove them, and especially because you're going to get hundreds of thousands of clusters. So you can sacrifice a little bit of the number to get a more pure set for cosmology, for example. Okay, so this may be, for now, this is still the beginning. We have, less than 20 systems, but we're increasing fast. But I would not be surprised that this could be like a great clean merging indicator. So like I mentioned before, ICL at very red frequency could be a very good max proxy because have all the accumulated stars that live forever as well. They would be there. We are trying to see, and we have already some of the data, if this also applies for FG, for the progenitors of fossil fuels. And in more concrete terms, we thought about doing for the mini JPass, but the problem with mini JPass was that the background, has been the super background correction, made it such that no matter what we got, we will not believe it, right? So, but the new guy, Mohammed, and I can't tell his family name. He's a great guy. He's very good. And he says this can all be redone. The question is time for him to do now because JPass is going to start in a couple of months, transition completely to full operation. And so this is a question for some of you. Any volunteers to do evolutionary track of the FG BCGs? Because we have the data, actually have actual spectra from Gemini and so on. That'll be great. So I think I talked too much. I'm going to stop here. Thank you.
Thank you very much, Renato. And the talk is open for questions.
Yes, maybe it's just a naive question, but regarding the problem with the powers in C groups, I was just wondering, I thought that I read that also the intracluster light fraction, relative fraction to the mass of the cluster could be an indicator of the age. So let's say that we have a heterogeneous sample where we have different ages, for instance. Do we expect the profile of the temperature to be in the central part really, really high and then see a cooling part, but in a, let's say, in a slower rate than for other groups, or just always hitting that central part?
Right, that's a great question. I didn't show you all the temperature profiles of all things that people call fossil groups, including very nearby ones that for us, would not be very good to observe. So there are two parts of the question. The first one is about age, and that's correct. If you see the ICL, and that's what I did a calculation for that particular cluster, 1007, I could say that this system had last merging at 5 gigayears ago. Okay, I could actually, comparing it to the one that's right below, relaxed, I could have an idea of how much ICL per year, the injection rate of ICL, I would expect just from orbital motions of galaxies there. So, but remember that I can only tell the age from the formation of fossil group of the system, but not for the whole thing. That's the age that I can do. But you have fossil groups you expect, the second part of the question, there are systems that have all the indications of fossil groups, but they do have cool cores. They're generally, the ones that I've seen, generally they're closer. And you'd expect that eventually, if there's no more merging happening, the last one heated up, that gas is going to cool off, right? Eventually, it's just a delay. And you find some that have very tiny cool cores, and there's one that is long, I think it's NGC 6842 or 6482, one of those. It's the closest to us. That has already a pretty well developed cool core.
And for that sample of the fossil group, is there any kind of observation about enhanced star formation in the central galaxy or even AGN activity, or not? Which again, I
would love to share a slide. I don't know if I can. After you stop the broadcast, I'll show you a slide. It's not even mine. It just came up with an interaction with some other people, and you know.
So, wonderful talk. What's the prediction you have for this circulation history of the fossil groups, what I would call BGGs, because they are groups, not clusters, right? So,
well, they are bigger than BCGs normally, so they are BCGs.
Smaller.
Yeah. No, they're bigger. The fossil groups are generally, not all of them, but they tend to be a little bigger. Some people think they're a little diskier, although
I mean, BCGs in fact may be even larger than groups, right? The largest BCGs are the non-clusters, not the non-fossil groups.
They are, in general, the fossil groups BCGs.
That was not the question. The question was the prediction on this circulation.
And that's what I'd like to see. If we had, I can see this in the gas, right? I should probably see this in the stars. So it would be interesting to see if you had I don't know exactly how this would work, some kind of secondary burst of star formation that matched, for example, the age that I'm calculating for the last merger from the X-rays.
So the example you have is any fossil groups?
Oh, so far we have in our system with Gemini data. Let's see here, because I can actually give the Gemini data before we actually do the X-rays, because we have data in different, for example, if you look at here, this is, where's Gemini? Gemini is here. So for this one, we had Gemini, we got it. For the first, let's see, oops. Oh, there's one missing here. We have one. A little, perhaps 1, 2, 3, this is 7, 8, 9, 10, 11. There's 11, including the progenitors. And what you see here, GN, we have the Gemini data. Sometimes we're missing the X-rays. This one, Oh, this one, Peppy. I think we have it, but it's not Gemini, so I have to find a way of reducing this. And for example, this one here, we had the 1231 from a previous work that we did. And we also have for the Cheshire Cat, it's a previous one work that we did, Jimmy and myself. This is actually a very interesting progenitor because it's the only case where you have two fossil groups merging that has been detected. It's a merging, it's a fossil group progenitor, but each one of the systems, since they're kind of on the line of sight, we could project the velocities. They're both fossil groups that are colliding.
That's because we're working in a sample of fossil groups of around 100 something.
Yes.
So with the STScI spectra and with a similar sample of non-fossil groups selected with the same criteria of being fossil.
Mhm.
And we've analyzed the stellar population history, and it's
Yeah, well, yes, okay. Yeah, I know the work. And in the beginning, they were different, then they were not different. I think there were 2 or 3 papers on that. There were possibly
we are
some different.
doing it right now, so it's
Okay, all right. So I think that's very interesting. The only care that I have there is that if the selection for a fossil group was made exclusively by magnitude, so you have other properties for the fossil group. Masses, they were low mass.
They are not low masses. I mean, they are expected to have higher masses. Among the highest masses. But you don't have actions for them.
Right. Concentration, for example, lack of AGN activity, and something like this. My fear is that I've seen many works, and there are many samples of fossils, right? And so people will start finding something, and then it becomes in the turbulent zone that there's no difference anymore. And my main concern in raising this sample is trying to avoid the noise, because if you dilute everything, and I'm sure there are many fossil groups, there are really fossil groups there, the problem is purity with this. I don't know exactly your particular work. I'm just talking about some work, Dos Santos, that works in the past. I was reading, and it was quite. It's difficult for me to actually believe sometimes results that people decide to say, okay, we're going to do delta mag 1-2, unless it doesn't work. We do delta m mag 1-4, and because people want to get a big sample, and they push a little bit here and there to do it, but inadvertently they end up putting more noise in the sample, So yeah, I'll be very glad to with the work you guys are doing. Yeah, it was very good.
Just one short question comment. What's the kind of what level of surface brightness that you need to be able to get the ICL?
The ICL.
Yeah.
Well, I guess maybe you remember the number from the HST that we got.
Well, not for the HST, but works say a number that is about 28 magnitudes per square second with arba. That is a number that is
Yeah, that's what I had in my mind. So do you have enough? I mean, deep enough data in JPass to achieve those songs?
We have to. We're gonna have to try. We may have to stack them. And the issue with stacking is again that you lose some information there. But we might in the beginning have to do stacking.
Very interesting.
So just a curiosity. Thank you, Renato, very talker. About you mentioned that for some person, the alpha iron ratio increasing and across radium. So is that that this change in relation to the cooling down of any model related to things?
So you're talking about
Yeah.
This.
Yeah.
Well, notice that we have very large bins here. Okay, we are scraping everything that we can out of there. So basically, everything here is in the center. It may not be the most central part, but it's everything kind of in the core. We talk about the 100 kiloparsecs here.
This is the idle, and then you have a table next.
No. This is not exactly this
fraction.
Right, but this is just the way. It could be the mass fraction. I could change this. It would be maybe just change a little bit the number up and down. I could calculate. It could be the silicon. Doesn't matter. There's we assume that there are only or at least two main contributions to metals in the IC. One is all kinds of supernova core collapse, which goes 1B, 1C, and supernova 2, hypernova, and the other one is supernova type 1A. Okay, so everything's going to be a linear combination of the production of these two systems. Sometimes the work that Rebecca did prior to that, which I can go into detail later, she was actually testing about 7,000 pairs of supernova models among themselves. Some are better, some are worse with respect to what we observe. But sometimes you find that there might be a third type of supernova there, but as long as it's not important enough, it doesn't really matter for this level of precision. Okay. Yeah, but here, what we're using here are many different elements that we're using, but in this case, it's not all of these, but it's oxyneon, magnesium, oxyneon, silicon, sulfur, at least. Okay, the other ones we could not, the nickel to iron, for example, is not that easy to get this because the fossil groups are hot, but they're not hot enough. The nickel, the main line of nickel is an AKV past the iron line. For hot clusters, it's great to see. For cooler systems, you don't see that. And then you have a little nickel in the L shell at 1 kV mixed with the iron. It's difficult to deblend that and get a clean abundance. So we don't use those that we get things that are too difficult to actually make. They're not correlate. They're not independent. So sulfur, silicon, oxygen, and sometimes neon, they are more or less clean. Then we use those ratios to infer something that we call the iron mass fraction from supernova type 1 and 2. It could be any element.
They're very high.
Yeah. Yeah. Well, the regular clusters are actually not that much, right? This is the regular cool core clusters. We compare to those. So when you compare to the fossil groups, yeah, and that's the interesting thing, because they are higher.
Questions? Okay.
Well, why is the need to get such a advanced measurement? I mean, I understand that there is something that is really very noisy because is there any possibility to an analysis of the systems looking at the luminosity function?
Oh, people measure the luminosity function of fossil groups. Well, they are basically, Lucas Johnson did, a few people did before. You can see this lack of bright galaxies getting to the center except for the BCG. There are some different studies of fossil groups. And again, that depends on how we select fossil groups, right? That have been studied in the luminosity function. Yeah.
Okay, but in any case, that will depend on value. High value.
Yes. Yes. Yeah, but the thing is that too is kind of arbitrary because it's I think the first fossil group was Trevor Pundman. They found, yeah, in I think 94. So yeah, and so you put sometimes a number because it looks okay, and later it becomes written in stone. This number could be 1.8, could be they're just they have this clear emptiness of bright galaxies near the BCG. So yeah, this is not something that one should be completely attached to it. What I think is interesting is that the way that Lee, for example, and Cheng did the simulations, their fossil groups, what they used was the ratio of mass, of stellar mass to mass of the halo let's see here. I don't have, I don't think I have here, but okay, I have here. And it was a much better definition, and but of course it's not easy to get. Here. So the stellar mass of the group divided by the mass of the halo is half than the average, what you find for normal groups. So basically, you have lack of stars there. And then they end up following the track of these fossil systems out there. So this is a good one. How do you know the mass of the halo? So you have to have some kind of other observations to be able to get that. It's not cheap.
It's going to have a system out of it. Get the mass to have some idea of the structure. That is something that, but well, if you have some lensing information.
Yes, exactly. Fair lensing, at least wide scale lensing, you could get that, sure. But fossil groups apparently they're very close. From my work on this, they seem to be really the most relaxed things you can get, and that's why my title is looking at the past, right? When you look in the past and get information about the future, because in principle they show us what every single system will become, given time enough. Yeah.
Are you aware of any work trying to extract fossil groups from inverted simulations to ensure that?
I know the old ones, but they, this is the most recent that I saw, Lian Chen, 2020, and they did a good job in that. It depends again how you define the fossil, right? Because if you use only the gap, magnitude gap, you have some works in the past. The simulations actually show that there's a correlation between the magnitude gap with the age of the formation of the system. There's several of them, at least two that I remember, they're very clear. But this is very different from what you observe, because you observe projections, right? So magnitude gap probably has to do with it. That's what I expect. But selecting a sample in the actual real sky based only on that, then it's going to be more noisy. So, yeah.
What if you level of galaxy having a living process? Okay, who's that? So that part of the that part of but you mentioned that after you can have some sort of what do you call it? So for speedy production, critical types instead of I don't know.
I'm not sure.
I mean, it's you mentioned that you have a double system. On the S2+1,
yes.
An additional amount of ICL, you have which way to decide that?
You just need to be galaxies rotating around one another. That's all, right? You can just have dynamical friction, you slow it down.
Okay, but by the
Yes, that's an interesting question. Yeah, I don't know at what point, because eventually, I'm assuming they would start stripping most of the stars that you had already in the galaxies there. And if you don't have any more merging or galaxy incoming, eventually this rate that I estimate for that system would start to go down, slow down. It would not be as fast as initially. But the rate was not that small. for that system. Okay, that system is at 0.1. My estimation of the last merger was at 0.4 in redshift. So during this time, it was this ridiculous number by a factor of 5. More ICL than mass. But keep in mind that more ICL than mass, if you're not growing mass, does not mean exactly the same, right? Because if you could have a ton of mergers, way more, you grow ICL, but you didn't grow mass as well. So the specific ICL may not grow so fast. When you have just a system without merging, the specific ICL is the one that shoots up. But eventually you may not have any more stars to strip. Right? It'll be an interesting simulation to do.
Okay.
Well, but that's the thing. One of the characteristics, Mirgali, or I forgot the name, isn't one of the references there. That people have been looking at the AGN activity in fossil groups, and it's generally none or tiny. They're not active, which is consistent with having a hot core, right? So you have the characteristics, the characteristics of all the characteristics of a cool core cluster. The abundance shoots up, everything, concentration, blah, except the cool core. And the AGN activity is correlated directly with the inflow of material, right? They have the cooling there. So it's not surprising, but they can't say that they're important there. And besides, this is also not because first thing that people would think is that AGNs may actually be hitting the core. Since the AGNs, they do hit the cool core clusters up to a level. If the AGNs had hit before the system there, but this is different because clusters have AGN, and some of them are amazingly powerful, and they still have cool cores. It doesn't destroy them. And fossil groups that you have the hot core, you have a very underdeveloped cool cores. So not clear what's the role of AGN there.
Okay, we can close the talk here.
All right.
Thank you very much.
Thank you. Tell me when you stop recording.
Yeah, just a second.